Hello everyone. Today we will learn about the power frequency characteristic of generator. I am the main teacher, Liu Qingping. So, what is the power frequency characteristic of the generating unit? We usually refer to the relationship between changes in the output power of the generating unit due to changes in frequency at the power. Frequency characteristic or regulation characteristic of the generating unit. It depends mainly on the characteristic of the speed control system. When the frequency change caused by the system load change, the generating unit speed control system will start to work to change the amount of steam or water inlet of the prime mover, adjusting the input power of the generating unit to adapt to the needs of the load power change. Let's first learn about the mechanical governor. Its principle can be represented by this diagram. When the unit's rotational speed decreases due to an increase in load, the opening of these two counterweights decreases, causing point A to drop to point A, and point C does not move, so point B drops to point B. Point D is the NDEF of the rotational speed setting element controlled by the servomotor, which does not change according to the rotational speed. So, due to the movement of points A and B, it causes points E and F to drop to point E and F, and the piston leaves, and the valve leaves with it, and the amount of steam intake increases, and this time the rotational speed goes back up. When this rotational speed rises, the counterweight opening increases again, in which case the points A, B, E, and F also change continuously. Then the changing process will not end until point C rises to a certain position, such as C. That is, when the valve opens to a certain position, the rotational speed of the unit restores the lever DEF through the opening of the counterweight to the position that makes the value of 2 completed closed, and at this time point B goes back to its original position. During the regulation process, point C goes up, so point A must be lower than point A. This means that at the end of the speed regulation process, the output has increased and the rotational speed will be slightly reduced. The governor spoken of here is a differential regulator. Here, we can achieve the purpose of translating the governor characteristic up and down by changing the position of point D by the servomotor. So, let's look at the second knowledge point, which is the power frequency static characteristic of generating unit. It is a curve reflecting the relationship between generator output power and frequency at the end of the regulation process, which can be expressed approximately as a straight line. We can take any 2 points on the characteristic curve. We define the static adjustment coefficient of the unit as R, equal to the negative triangle F divided by triangle PG, where the negative sign indicates the change in the generator output power, which is opposite in sign of change in frequency. Similarly, the static adjustment coefficient of a unit is usually expressed as per unit. That is, R is equal to the negative per unit of triangle F divided by the per unit of triangle PG. It is also equal to the negative triangle F or Fn divided by triangle PG or PGN. This expression can be converted to obtain the static regulation equation of the generating unit. In addition, we often use another coefficient called the power frequency static characteristic coefficient of the generating unit kg. It is the reciprocal of the adjustment coefficient R, unlike the frequency regulation effect coefficient KL of the load mentioned earlier. The static characteristic coefficient Kg can be artificially adjusted and set. However, its magnitude, that is, the adjustment range, is limited by the unit's speed control mechanism. Generally speaking, generators of turbo generating unit have a 4 to 6% adjustment coefficient, while hydro generating units have an adjustment coefficient of only 2 to 4%. So, what is the relationship between the regulation characteristic and the active power distribution? Between the units, we can see this diagram for two generators operating in parallel. As the system load increases and after governor regulation, the frequency of the system stabilized at F1. The load of unit 1 is PL and increases by triangle P1. The load of unit 2 is P2 and increases by triangle P2. The sum of the increments of the two generating units is triangle PL. We can get the following equation from the static regulation equation of the generating unit, derived earlier. From this equation, can obtain such a conclusion. When the power increments expressed as per unit, the power distribution between generating units is inversely proportional to the unit's regulation coefficient and proportional to the unit's regulated power. If the adjustment coefficient is small, then the load increments taken by the unit increases. If the adjustment coefficient is large, then the load increment taken by the unit becomes smaller. If there is no generator with regulated capacity in the system, then the unit's regulated power is zero. If the governors of all units are differentially regulated, then they all undertake the load fluctuation. The last point to learn is the Mohr-Function of the regulation characteristic. So, how does the Mohr-Function form? It is mainly caused by the insensitivity of the measuring element, which does not react to those small changes in rotational speed, especially in mechanical governors. Therefore, the governor has a certain Mohr-Function. Thus, the regulation characteristic is actually a band with a certain width, rather than an ideal straight line. The width of the Mohr-Function can certainly be described in terms of the Mohr-Function degree, where triangle FW is the maximum frequency error that the governor cannot discriminate. So, what effect does the Mohr-Function zone have on the system? Because the frequency regulation characteristic of the governor is a band, it leads to a certain error in the distribution of active power among the generating units operating in the parallel. corresponding to a certain mole function degree, such as the relationship exists between the maximum error power and the adjustment coefficient. This derivation is done by looking at these formulas below, so we will not derive them one by one. We derive the equation for the relationship between the maximum error power and the adjustment coefficient, from which we get these two conclusions. The first conclusion is that the maximum error power, triangle PW, is proportional to the mole function degree and inversely proportional to the adjustment coefficient. The second conclusion is that, although the existence of the insensitive interval causes some power error or frequency error, this insensitive interval should not be too small or completely absent. Generally speaking, the insensitive interval of turbo-generating units is 0.1% to 0.5%, and the insensitive interval of hydro-generating units is 0.1% to 0.7%. In this lesson, we mainly learned the basic principle of generating unit governor, generating unit power frequency static characteristic, and adjustment coefficient, the relationship between the regulation characteristic and distribution of active power among the units, mole function dawn, and other knowledge. So, that's all for today. Thank you.